Hey, Hybrid, here is your review day for your summative. We all take our summative tomorrow. Take a second to kind of think about what topics do you feel that you need to practice. Okay, so we're going to go through all of these. I'm going to try to go through it very quickly so you guys can study and practice whatever skills you need to work on for tomorrow. Anything you're confused on, I can talk to you tomorrow about before the test, but I want to give you as much time as possible. Okay, so it is exponentials and exponential functions. Okay, the first page here, we are converting from radical to rational form. So let's go through these very quickly. Okay. Um, for each section, you can pause and then check the answers. I'm going to kind of pause in between so you guys can do chunks at a time rather than going through everything by with me. You can do some of it by yourself. So the first one, if you have a missing exponent, so for example, this one here, there is an imaginary one inside there. We know our base is x, and then we got to stand that fraction up. So that becomes the 1/3 power. And remember, the cube root is always to the 1/3 power. Okay, this one, y is my base. And if I stand that function up, I get to the 3/4 power. This one, there is an imaginary one with this y, so that would be y to the 1/4 power. For this one here, there is an imaginary 2 in the front because it's the square root, and square root means something times itself, two numbers, right? So it would be 3x to the 3/2 power. Be careful, guys. You have to put those parentheses there. Otherwise, just the x is raised to that power and not the 3x. Okay, same thing here. So we have a 1 on the inside. Notice this one's written differently. So in this one, the 2 is not raised to the first power. So the 2 is just going to sit in the front, and then it's going to be x to the 1/3 power. Okay, in this one here, we have 2x as our base to the 5/3 power. And then I would put that in parentheses because it's appearing in parentheses there as well. Remember that 5/3 could be distributed to the 2 and to the x. Okay. We're going to go and do the other way. So this time I have to take my base and put it inside of my radical symbol. Whatever is on the denominator goes on the outside, and whatever's on the numerator goes on the inside. So I don't really need to put the 1 there because that is an imaginary number. So really it's the 4th root of 5. Okay, if you want to, you can put the 1 there, but you know the 4th root of, whoops, 4th root. I'm not going to write it like that because that looks like 4 times the square root. The 4th root of 5 is really what we would say. All right, this one, m is our base. It would be the 5th root of 7. M to the 7th. Okay, so this one, I see the parentheses around 2m, so 2m is going to go on the inside, and it would be to the 3rd root. There's an imaginary 1 after the m. Notice number 10 looks just like number 9, but without the parentheses. So what that means is inside our radical, the m goes, it's the 3rd root of m, but it's being multiplied by 2 in the front. So the 2 is not underneath like it is in number 9. Okay. For number 11, we have xy underneath because it's in parentheses. And if you want to, you could put these ones in parentheses underneath if that keeps it so you know which ones go underneath and which ones do not. That's fine. This would be the 8th root. And then looking at 12, very similar to number 11, except for x stays on the outside, and it's the 8th root of y. So 9 and 10 are very similar, 11 and 12 are very similar. Okay, so let's look at the next one. Okay, this is exponential functions. Determine which functions are exponential. Go ahead and pause the video and see if you can do this section. All right, so if it is an exponential function, we're looking for a common ratio. So really we're looking at the y's because it looks like the x's are all counting by ones. So to get from 0 to 1, 1 to 4, 4 to 9, and so on, is there something I can multiply by to get from one to the next? No. Okay, so this one is not geometric. For the second one, 1/3 to 1, 1 to 3, and so on. Yes, it is. So this one, the R value is 3. So that is definitely exponential. The next one is a little hard because of the fractions, but if you test it out, you use that dividing thing that we talked about yesterday with our geometric sequences. If I do 5/2 divided by 5, I get the R value of 0.5 or 1/2. So yes, that is also geometric. Basically, I'm multiplying by 1/2 every time. And the last one, there's nothing that I can multiply 4.5 by to get 4 and so on. So that one is not exponential. It's not increasing by a common ratio. When it comes to this one down here, be careful because it is counting by threes. They did that just because the numbers get very big. Again, use your calculator and you can put in 3 to the x power and y equals, and then look at the table. If you do that, you get these values for for y. And then you can do your best graphing these. Of course, the right-hand side, 0, 1 I can do. It's gonna be like down here. 1, 3, 2, 9, and 3, 27. And the rest are all going to be really, really close. They kind of skim the x-axis and go up. So it's something like that. Okay, we had a lot of these yesterday when we talked about our transformations. Domain is all round numbers. Range is all the ones that are greater than my asymptote, which is 0. As x goes to the right towards infinity, our graph is going towards infinity. As x moves left to negative infinity, our graph is getting closer to our asymptote, which is 0. The y-intercept is 0, 1. So whatever x equals 0, that's our y-intercept. And the asymptote is y equals 0. Okay, here is the next one talking about exponential functions. This one you're going to use the regular exponential function. So we are looking at this equation. Okay, because it's talking about the regular function. Go ahead and pause and see if you guys can figure this one out. All right, so looking at the table, my initial value or my y-intercept is 0, 4. So my y-intercept, I'm just going to put 4 down. My constant ratio or my common ratio, what's happening every single time? Well, it looks like it's decreasing by 2, which means I'm multiplying by 1/2. So if I'm writing my equation, okay, I have to fit these two pieces in for A and for B. So my equation would be f of x equals my starting point is 4 times my common ratio is 1/2 to the x power. Okay, if you type that into y equals and then look at the table, it should match what you have in this table here. All right, for the next one, I'm going to show you guys how to work smarter, not harder on this one. We're comparing two functions. The f of x function is an exponential function. The g of x is a linear function. So we're going to make our own little table here. We have f of x and we have g of x. Okay, and we're going to test out all of these x values that are here in the table. Okay, so we're going to say when x is -1, when x is 0, when x is 1, 4, and 10. Now you could sit here and you could use your calculator and substitute. So you could put -1 in for the x and the f of x function and figure out what it is. And then do the same thing for the g of x and see what it is. But we're going to use our calculator to do this instead. So I'm going to go ahead and get my calculator out. I'm going to clear out what I have in y equals. And I'm going to put both functions in. So the f of x function is 3 to the x power. So I'm going to put that in, 3 to the x power. And I'm going to hit enter. And in y2, I'm going to put that linear function, which is 4x. What is it? 4x plus 3. Okay. If I go to my table, second graph, notice how I have two lists here. I have Y1 and Y2. I'm going to go down to where those numbers were. So we were talking, our very first numbers, they're all in this area here. Okay. And this is what I'm going to copy over or look at when I'm looking at this question. So in a minute, I'm going to copy these over because that makes it easier instead of looking at two different screens. This is where those numbers are coming from. Okay, so according to that, I had 0.3 repeating and -1. I had 1 and 3. I had 3 and 7 and 81 and 19. And finally, ooh, huge number, 59049 and 43. Okay, so what this question is asking us, it says, when will g of x be greater than f of x? So I want to know, when will this column here be greater than the other one? So if I look at the first one, 0.3 is greater than -1. So that is not true. G of x is not bigger. In the second one, 1 and 3, 3 is bigger. So x equals 0 is one of the ones that make this true. And the next one, 7 is bigger. So 1. And this one, 81 is bigger, and this number is bigger. So the only ones where g of x was bigger than f of x was in B and C. That saved me a lot of time. I didn't have to sit there and substitute and fill this table by hand. I just used my calculator. All right, so here is a big one we're going to see. Lots and lots of rate of change. Remember, rate of change is slope. So they give me two x values. They say 0 and they say 4. So I'm going to kind of set this up as my basis. All right, now I'm going to do some substituting. 2 to the 0 power. Well, anything to the 0 power is 1. All right, 2 to the 4th power, 2 times 2 times 2 times 2. Well, that's 16. Now I can follow y2 minus y1 over x2 minus x1. So let's go ahead and do that right now. I'm going to set up my basis of this. I'm going to fill in the blanks. My y2, my second y is 16. My first y is 1. My second x is 4. And my first x is 0. If you need to, you can label those x1, y1, and all that. So I get 15 over 4. And if you divide that out, you get a rate of change of 3.75. A rate of change is just slope. All right, exponential growth and decay. This problem is difficult. You're going to see one just like this on your summative tomorrow. So this is a part A and part B. It's probably worth about 4 to 6 points. Okay. It says the population of city in 2000 was 2,800 people, or 28,000, sorry. By 2006, the city's population had grown to 47,200 people. Assuming that the population has grown linearly, I'm going to underline that, since 2000 and continues to grow at the same rate, what would the population be in 2010? So since it says linearly, I want an equation in y equals mx plus b form. Okay, which means I need to know a slope and I need to know a y-intercept. Well, the y-intercept is easy because we know they started at 28,000 people. To find slope, we're going to think of two ordered pairs. Okay, so if I set up what in 2000, the population was 28,000. In 2006, the population was 47,200. Now I can do what I did in the last problem, my y2 minus y1 and my x2 minus x1. So 47,200 minus 28,000. That gives me, let's see, 19,200. And 2006 minus 2000, that gives me 6 years. So if I divide that, I know my slope is going to be 3,200. Okay, so now I can take my slope and my y-intercept, which I know was 28,000, and I can write the equation. Y equals 3,200x plus they started with 28,000 people. Okay, so then it says, if you look at the question, what will the population be in 2010? Well, if we're talking it started in 2000, 2010 would be 10 years. So I'm going to substitute 10 in for X. And if we do that, you get approximately, it's going to round a little bit, it's around 60,000 people. Okay, we had to round because we cannot have partial people. So you had to find the slope, you had to find the y-intercept, write the equation. All right, this is the one where it gets a little funky. Write the appropriate exponential model for the population. So we're talking about the regular exponential growth model here. So looking at this, we know where it ended. It ended when there was 47,200 people. Okay. Our initial amount we started with was 28,000 people. We don't know the growth rate at all. So I'm just going to put B in there because we're not sure what the growth rate is. But we know it says time since 2000. Okay. Well, we were talking about a period of 6 years here, right? From 2006 to 2000. So that is to the sixth power. Okay. So I put in all the information I know. The ending population, the initial amount, we don't know the growth rate, and we know that it was over a course of 6 years. So looking at this, I need to solve for B. So the first thing I'm going to do is I'm going to divide to get rid of the 28,000. I'm going to divide. Okay, so those cancel out. B to the sixth power equals, looks like 1.686. And then the last thing I need to do is I need to get rid of the sixth power. So really I need to take the sixth root of both sides. So go back to your calculator on this one. We want to find the sixth root. So if I go back to my main screen, second mode will get me back to the main screen. If I hit math, I know that option number, whoops, go back. Boop, boop. Option number 4 is the third root, but right underneath of that is the fifth root. That's what I want. Okay, I want the sixth root. So I'm going to hit 6, and then I'm going to hit math, option number 5, and that makes it the sixth root. And my number was 1.686. And if I hit enter, I get roughly 1.09. So that means that my growth rates R equals 1.09. That's my missing piece. Now I can write the exponential model. F of x equals my starting population times my rate to the x power. So you had to do a little bit of calculations to find the growth rate because that was not given to us. Okay, so if you substitute everything you know, you can get the parts that you need. All right, this one is exponential decay. I can tell because it says it depreciated. So we're going to use the exponential decay model for this one. So if you remember that one, our starting amount is 10,000. Decay is 1 minus, and it's 10% as a decimal is 0.10. And we want to do to the eighth power because we want the eighth 8 years later. Okay, you can simplify this if you want. This here becomes 0.90 if you want. And if you put that all in your calculator, your final answer is $4,304.67. Okay, this one is also exponential decay because I see it's decreasing in size. So we have A, we're starting with 100,000 and it is 1 minus, our rate is 2%, so 0.02 and is 100 years to the 100th power. Again, if you want to simplify that, you can. That simplifies to 0.98. And if you've done this correctly, your answer, whoops, we're not talking money here, we're talking people. It is a decimal, so I'm going to round it to the nearest person, which is 13,262 people. So in 100 years, they went from 100,000 people down to 13,262 people. So anytime you're talking about populations or value of something depreciating, that's when you're going to use your exponential growth and decay model. All other ones, you're going to use your normal exponential formula. All right, this one, we're talking about comparing two banks. And I see some keywords. I see where it says compounded monthly. Compounded monthly. So this tells me I'm going to use the compound interest formula. This one's actually comparing two different banks. I'm going to call it Bank A and Bank B, just so I can compare the two. We're going to do this for both. So the first bank, if I fill in the compound interest formula, I have A equals, we're starting with 100,000 and our rate looks like it was 6.25%, which is 0.0625 as a decimal. It's compounded monthly. There are 12 months in a year, so I got to put a 12 there. And don't forget, another 12 in the exponent times the amount of time. And it says that one we're going to keep there for 3 years. My second equation, okay, I'm also starting with 100,000. Okay, and it's growing at a rate of 1.25%, which is 0.0125. It's also compounded monthly, so I'm going to put 12 in the exponent and the denominator. But this one is going to be in there for 15 years, so we're multiplying it by 15. Go ahead and pause your video and see if you guys can calculate which one. Calculate both of them and see which offer he should take, Bank A or Bank B. All right, if you've done this correctly, Bank A, in the end, after 3 years, you will have $120,000, 564.35. So $120,564.35. Bank B, if he takes that offer, he's going to have $120,611.25. So which option should he take? They're both very, very similar, but he should take Bank B because it's greater. All right, we got a couple more to go, so let's keep on going. Write an exponential decay function for them to model this situation. So they tell us the initial value, they tell us the decay factor, and they give us from when x is between 1 and 4. So let's set up the equation, and then we're going to figure out the rate of change, which is the slope between those points. So if I'm writing a function, f of x, my initial value is 49, times my decay factor is 0.7. Okay. And it's to the t power, or you can say x power if you want, but t stands for time. All right. If they want between 1 and 4, I'm going to go ahead and set up that structure. Those are my x values. All right. Now we're going to substitute. If I put a 1 in for t, I'm going to get 34.3. If I put a 4 in for t, I'm going to get 11.7649. It's a little long there. And then I'm going to do y2 minus y1. So 11.7649 minus 34.3. And my x2 minus my x1, which is 4 minus 1. So you should end up with negative 22.5351 over 3. which is -7.5. That's our rate of change. Okay, I would recommend trying to keep your decimals as long as possible. Don't round your decimals until the very end. Otherwise, you're going to get a different number. Okay, geometric sequences. This one should be quick and easy. We're saying, is it geometric? If so, what is the common ratio? All right, so for this one here, it looks like it's increasing. Yes, it is. And the R is 5. We're increasing by multiplying by 5 every time. This one here is also geometric, and the R value is -6. You can see that pattern where it alternates negative, positive, negative, positive. So that tells me that my R value is negative. All right, here, this one here is also geometric. And the R value is +5. The last one's also geometric. They're all geometric on this page. This one, if you divide them out, do the second divided by the first and so on, you get an R value of 1/3. Okay, on to the back. All right, they give us the sequence. We have to write the explicit formula for geometric sequences. That's the only one we need. Okay, so if you need to, look at the backboard for the formula. Okay, so we're going to start with f of x equals, our first term in the sequence is 5. Our common ratio, if we look up here, what's happening every single time? Well, it looks like it is multiplying by 2. So 2 is my common ratio to the n minus 1 power. That's all I have to do. Okay. Or instead of writing f of x, we probably should have written a sub n. That's fine. You can do either one. A sub n. That's more like the actual formula. All right, then I want the 6th term. So I want to find a sub 6 in the one above. So I'm going to rewrite it. I'm just now replacing the n with a 6. Well, 6 minus 1 is really 5. So this is saying 5 times 2 to the 5th power. 5 times 2 to the 5th is 160. So the 6th term in the sequence would be 160. Okay, so for this last one, you would need to graph them and you need to tell the transformation. Okay, so for this one, I'm sure you guys could use your calculator. You could graph it, you could figure out the tables. I'm going to jump down to what happened in each one of these. Okay, so looking at the original function, I'm just going to write it again so we can see it all in one. All right, the 3 made it stretch by 3. And then -1 at the end made it go down 1. Okay, this one over here, the function was f of x, 2 to the x plus 3. This one, 2 to the x, is the parent function. The only thing that happened was this went up 3. Okay, so if you guys finish this early, there is a geometric sequence worksheet that you can work on, or if you did not finish your compound interest one from yesterday, you're more than welcome to complete that. If you have any questions, you can either email me through Schoology or you can save it for tomorrow right before the test. I can answer any questions that you may have. All right, have a great day.